All right, I think we are recording. Okay, almost made it through the first week of the semester and the first week of Engineering 213. So let's talk a little bit about logistics. First off, how'd the homework go? Not too bad, right?
It wouldn't show me my score after I was finished. I had to go to the grade advocate to see that.
It should show it now. Yeah. Typically, what'll happen is, and that'll typically be the case for most of the assignments, especially the ones where we're uploading scanned PDFs, because somebody will have to go and grade it. So what'll happen is, so if you have a homework assignment due Monday, let's say, it probably won't be graded until Tuesday or maybe even Wednesday. So that's sort of why I set it up that way, but I don't have a problem changing that for 1.2. It's not too big of a deal, but it shouldn't be that all that bad. Okay, the lecture from last, or the recording from last lecture did work. At least I think it did. I checked out the audio. It seemed to work out a lot better. I uploaded that to YouTube. It is linked to the YouTube playlist. I don't know if anybody had a chance to check that out or if the audio worked out well, but if somebody could just take a couple seconds and check that out and see if everything worked out well, it'll be good. Okay, attendance grades. I haven't yet uploaded attendance grades. I will probably do that either after today's lecture or between now and Monday, simply because I know today is the last day to add and drop classes, so for all I know, we might have somebody who tries to register at the last minute, so it's a little easier the way that I deal with attendance to do it once the roster is sort of set in stone, as it were. Okay, so homework 1.1 was due at 8 a.m. this morning, and so homework 1.2 is going to be assigned today. It's going to open at 9 a.m. and it'll close, or it'll be due next Monday at 8 a.m. via Blackboard. It is going to be similar to to homework 1.1 in the sense that it's a timed quiz, or an untimed quiz, I should say. But this will be the last one where it's sort of in this like quiz fashion. The rest from here on out are going to be uploadable PDFs and whatnot. And we'll talk about that as we get to it. All right. Sound good? Okay. So, any questions? Okay. So what we're going to do today is we're going to continue our discussion of dimensions, and I had introduced the concept of dimensional analysis. So basically what dimensional analysis is taking a given expression and trying to figure out whether or not it is dimensionally consistent. In other words, do the values add up appropriately? Do they multiply appropriately based on the input units and the terms in the expression? And then I'm going to do a really brief review of math. And when I say review of math, I want to just sort of give you a big picture suggestion of the stuff that you need to know how to do to negotiate Engineering 213. And I'm going to talk about three topics: algebra, trig, and calculus. And of those three, the one that is the most important, bar none for this class, is the trig. Okay, it's not hard, but there are going to, you're going to be dealing with sine, cosine, tangent, and solving triangles and whatnot fairly soon. So I want to make sure that you're up to speed on that. Okay, so let's go back to our dimensional analysis discussion. And we didn't quite get to this example, so let me sort of set the stage. So in our last lecture, we discussed the concept of dimensional analysis, and I showed you an example of a very well-known formula in engineering, and that is if you have a simply supported beam and you apply a load at midspan, that beam will deform, and you can compute the amount of deformation at midspan, with that PL cubed over, 40 ADI expression and so on and so forth. Now, the point of dimensional analysis was to basically look at that formula and go, if I input units according to that expression, am I going to get a resulting output that makes sense? Okay, and so I kind of gave you a real brief overview of that in that last example, but today I want to actually go through one with you to kind of show you how that works. So what we're going to do is we're going to look at this expression right here. So this is something that you all are going to be dealing with at some point during your engineering education. This comes from the land of fluid mechanics. So this is how you compute the total amount of energy in a fluid conduit, like a pipe or whatnot. And the energy in a fluid conduit essentially comes from three areas. It comes from the pressure. So we express energy in fluids land in terms of this term head, and it comes from three components. We call this the pressure head term, We call this the velocity head term. We call this the elevation head term. And those concepts, I think, should kind of make sense. I mean, think if you had a pipe filled with, let's say, water, you're going to have more energy stored in that conduit if the fluid's at a higher pressure, right? You're going to have more energy if the fluid's moving faster at a higher rate of speed or a higher velocity. And as for the elevation, I mean, if you've ever been swimming, the deeper you swim, the more pressure you get, right? So we tend to, it might seem kind of odd, but we tend to actually express energy in terms of distance, like feet or meters. So it's, for example, if you've ever seen a town that has like a water tower and whatnot, like the fundamental calculation you're trying to figure out is how tall does that thing need to be to supply the appropriate amount of energy to the municipality and whatnot. So energy in terms of feet might be a new concept, but it'll something you'll have a lot of familiarity with when you start going into the land of fluid mechanics and whatnot. So what we're going to do is we're going to take this expression and we're going to take these terms and we're going to plug them in and see if this is dimensionally consistent. And you'll see what I mean about that here in a second. Okay, so let me get out of this. And I think I changed my settings here on the notebook that it should be a little easier to navigate for me. Okay, so here's our expression, and what we're going to do is we're going to evaluate this term here, and we're going to evaluate it solely from a units perspective, okay? And what I mean by that is I'm going to plug these, for each of these terms, I'm going to plug in their associated units to see if they're dimensionally consistent. So one of the things we're going to talk about is like what happens with this 2 and so on and so forth. And then when we talk about dimensional consistency, you'll see what I mean here in a second. Okay, so let's rewrite this expression down here. So we have, here, let's do this. Oh yeah, that setting on this monitor is a lot better. Okay, this is P. This letter here is the Greek letter gamma, and in a lowercase form, it kind of looks like a letter Y. We tend to use Greek letters a lot in engineering land. The term gamma is pretty commonly used for unit weight, like a unit weight of a material, like however many pounds per cubic foot or newtons per cubic meter, what have you. Plus V squared over 2G plus H. Okay? Now, what I'm going to do is I'm going to go into each of these terms and I'm going to substitute the appropriate units that would be associated with these. So let's take a look at this. So let's look at the first fraction. And so the top of this is expressed in newtons. Okay, so we have, or sorry, newtons per meter squared. So what I'm going to do is I'm going to write that like this. We'll maybe write it like this. And then that's divided by this term gamma, which is newtons per, let me do that a little bit more formally. Like that. Okay. Now what we're doing is adding the next term. So what do we have here for this next term? So we have velocity squared. Okay, so velocity squared. And we're going to say m divided by s squared. And now we have 2g. Okay, so first off, let's deal with the g. So g is meters per second squared. But then let's talk about this 2. Now, from a dimensions perspective, let's think about this for a second. Okay? If I have 10 feet and I double it, what do I have? 20 feet. Does that change anything from a units perspective? Really? Not really, you know. So these constant terms, I mean, we can consider them if we want, but from a dimensional analysis perspective, they're not really going to affect anything. So if I'm going to be honest, if I'm looking at this solely from dimension standpoint, I'm just not going to worry about that 2, okay? Now, that's different than considering, let's say, this square, right? Because if I take 10 feet and I square it, I get 100, but I get 100 square feet. It's a different unit system. Does that make sense? I'm not really going to worry so much about constant coefficients, but operations involving squares and things like that, that's not really going to affect things very much. Okay, and finally, we have this term h, and that's going to be in meters. And let me scroll down a little bit. Oh, goodness. Okay, does that make sense? So far, so good? Okay. All right, now let's see if we can simplify this thing a little bit. Now, I've got 3 terms, 3 fractions here, so let's deal with each fraction one at a time. Let's start off with this one. Okay, I don't really like the way that this is written out. I'm going to write this out in a little bit of a different fashion, and you'll see why I'm doing this. So, would you agree with this? Would you agree with that? So, this fraction divided by this fraction. And the reason I wrote it this way is because do you remember how to handle when you divide 2 fractions? You flip and multiply, right? So that's why I wrote it this way. I think it's a little easier to assess. Okay. Plus, now let's see if we can handle this one. Okay. Now, we have meters per second, but the quantity is squared. So this is going to be meters squared over second squared, and then we are dividing that by what's on the bottom. And then plus meters. Okay. All right. So I wrote it this way. Maybe I ought to do something with it. I'm dividing these fractions. Maybe I ought to flip and multiply. We'll see what happens there. So, oh, forgot my brackets. I kind of like using these brackets here to sort of make the point I'm doing a dimensional analysis. Multiplied by let's do the same thing over here. Okay. Now I think we can start doing some stuff. What can we do? Let's look at this internal parentheses. Let's look at this first term. Is there anything I can do to make this a little simpler? What about the newtons? What can I do with that? They cancel. So these cancel. All right, so I can handle that. By the way, if for some reason, if I ever write something and the handwriting is a little off, like you can't understand what I'm reading or writing, please tell me. I will take it personally, but I will fix it. That was a joke. All right. Okay. Now I have meters cubed over meters squared. So what's that going to result in? And basically just meters, right? Meters over 1, which is meters. All right. What about this term over here? Okay. So what about the seconds? What's going to happen with that? They're going to cancel. And then meters squared over meters. And then plus meters, right? So we're at this point. Let's go back to the initial question. Is this dimensionally consistent? Well, let's ask it this way. What is 2 feet plus 3 feet? 5 feet, right? What is 2 feet plus 3 hours? That doesn't make any sense, does it? Right? that would be, if I asked you what is 2 feet plus 3 hours, that's not dimensionally consistent. That doesn't make any sense, right? So the question is this dimensionally consistent? Let me ask it to you this way. What if we had gotten m plus, I don't know, m squared? Let's say we did our dimensional analysis and that is what we were left with. Would this be dimensionally consistent? No, it wouldn't make sense, right? You can't add square meters to meters because they're representing different terms. One's representing area, one's representing length. But here in this expression, when we went through and carried it out, we end up finding that we plug in these pressures and velocities and gravities and all these things, but in the end, when we chug it all out, we're taking meters, meters, and meters and adding it up. So is this expression dimensionally consistent? Yes. Yes, it is. So absolutely, yes, this expression is dimensionally consistent. And think, all I would have to do to make this expression not dimensionally consistent is, what if this was h squared? You know what I mean? What if this was velocity cubed? What if I didn't have a gamma here? These are, let's be clear, in engineering, sometimes there are some formulas here and there that are kind of long. And so you as an engineer need to be able to, every now and then, take that expression and decide, does this make sense or not? And so that's why we're doing this, because it's pretty natural to the science that we're doing. Okay, any questions? All right, so one of your homework problems is going to be a similar dimensional consistency question. I am going to give you a slight hint on the homework assignment to make your life a little easier. That's what the definition for a Newton is. A Newton is a kilogram times a meter per second squared. I didn't explicitly state that on the homework assignment, but you do need to use that in order to assess the question at hand. Any questions? Okay. Let's go back to lecture land. Do I need to leave this up for a second? Okay. So, whenever I developed my teaching philosophy, I think I mentioned this to you on lecture one of the first things I did is I looked at all of the stuff that I didn't like that my professors did over the years that I was in college. I said, I'm not going to do that. And one of the things that always used to bug me is stuff like this, is that when we would have a problem in class that would be pretty simple, and then the homework assignment comes and it's this ridiculousness. It's like, we didn't cover this in class. Or, in class, homework is 1 + 1 = 2. The test, calculate the volume of the sun or some craziness. It's like way harder than what we covered in class. I don't like that. I don't want to do that. And so what I have found in this class, teaching it a number of times, is that the actual concepts that we cover in here are pretty easy to understand. They're not tricky. Okay, this isn't a tricky class. There's calculations that you need to do and there's steps that you need to follow, but the fundamental basics of what we're talking about are pretty easy to wrap your head around. But it involves math. And I have found that it's not the statics that trips people up, it's the calcs every now and then. So I want to, in one fell swoop, pretty much go over every math skill that you need in order to negotiate Engineering 213. And I'm going to cover 3 sciences, algebra, trig, and calculus, but I'm really focusing on the trig. Okay, so let's talk about algebra first. So first off, you do need to understand basics of, the operations factoring. Like, you need to be able to do something like this. That If I have A times a quantity B plus C, that's AB plus AC, okay? It's not AB plus C or what have you. Make sure that you understand that. I think that should be pretty fundamentally basic. The quadratic formula, we will probably use that here and there in the class. This one, we're actually going to do a fair amount of. Now, this one, I imagine it's been a while since you've done a problem like this. I've got to believe that you have, though, right? That you've been given two equations and two unknowns, and you have to find that magic value of x and y that satisfies both equations. I've got to believe you've done something like that before. It might have been high school, or maybe you did it in Math 127 or what have you, but you've seen stuff like that before, am I right? Okay, so it's this one, I imagine, is a little bit more, I don't know, it's been a while since you've done it. I imagine this is a little bit more fresh in your head than this. So when we get to the point that we are going to talk about this, I have some specific examples dedicated just to this. One thing I will say about this type of problem right here, and we will deal with them in here, just about everybody in here should have a calculator that will do this for you. Okay, this isn't a math class, this is an engineering class. Okay, and I'm not averse to utilizing the tools available to you to perform this stuff. So, you know, I joke around about the Casio, but if you have pretty much any scientific or graphing calculator can do these problems for you. Okay, so one thing I will say, if you aren't yet, I haven't explicitly said this, but if you aren't yet in the habit of bringing a calculator to class, start doing it. Okay, because we are going to be at certain points during the semester, we are going to be going through stuff like this, like how to do this on your calculator. I have my slides particularly focused on how to do problems like this with the Casio, which is what we typically use in Engineering 111. But what I will probably do is post I think I did this last year, I posted a playlist on Teams that had how to solve problems like this for like a wide assortment of calculators, because I imagine some of you have TI-89s or TI graphing calculators or Casios, HPs, what have you. So I collected a big list of them, and I said, okay, here's how to do it for each of those calculators. So, okay, trig. Okay, most of this is going to talk about trig. We're going to start simple, and then we're going to work our way into some of the more rigorous concepts. So first off, you know, trig, you know, obviously we're primarily dealing with triangles. So first thing, just make sure that you know that if you have some triangle with three internal angles, A, B, and C, that those angles add up to 180 degrees. I'll be honest, I probably won't use some of this terminology throughout the semester, but I do want to make sure you're familiar with it. So for example, complementary angles, the idea that two angles sum up to be 90, or supplementary angles, the idea that two angles sum up to be 180. And then, you know, you might have some geometry problems here and there throughout the semester where you have a situation like this, and you should know that if I have two parallel lines that are cut by a transversal, that angles 1, 4, 5, and 8 are all equal, and angles 2, 3, 6, and 7 are all equal, right? I gotta believe you've seen that before in high school geometry or trig or whatnot. That should be pretty familiar, right? Okay, all right. Okay, so basic trig functions, sine, cosine, tangent. You probably heard the term SOHCAHTOA, right? So we know that given a right triangle, you know, here's our right triangle, and for an angle in question, we can define three trigonometric functions. Really, two of them are unique, and that's the sine and the cosine. Sine and cosine we will use most readily throughout the semester. The idea is that given this angle, we can reference that the sine of the angle is the opposite over the hypotenuse, and the cosine is the adjacent over the hypotenuse, tangent obviously being opposite over adjacent. The reason I say that we use the sine and cosine more readily is because when we start investigating the usage of vectors to represent forces and whatnot, typically what we will do is take that vector and split it up into x and y components. We do that using sine and cosine. We don't use tangent all that much, but yeah. One thing I will say, make sure that you're being diligent in ensuring that your calculator is in the appropriate mode, you know, radian mode versus degree mode. So, like, I won't micromanage how you do that, but that's the type of thing that can cause you to have calculator errors and whatnot throughout the semester. Pythagorean theorem, we know that A squared plus B squared equals C squared. I gotta believe that's pretty familiar. So far, so good? So I'll level with you. I don't have an example in class, but I do have a problem. So problem 2 on your homework assignment, I'm giving you a right triangle. I'm giving you an angle and one of the sides and having you compute the length of one of the other sides of the triangle. And I've got to believe that that's pretty basic, pretty fundamental. Everybody okay with that? Okay, well, I mean, we can make up some numbers and go through an example with you if you like, but I think that's pretty straightforward. Okay, this one is going to be used quite a bit. Now, let me say this. When we get to this point, we are going to discuss this explicitly. So it's not as if on day 1 I'm expecting you to remember all of this, but just know that we're going to be doing this a lot. This, however, is not really anything that's all that conceptually different from what was on the previous slide. I mean, this is a right triangle. This is essentially a right triangle as well. I mean, here's the 2 legs of the triangle. Here's the hypotenuse. Here's an angle. And this is just, Pythagorean theorem, sine, cosine, and so on and so forth. But the point is that a lot of times what we will do is we will take a vector, again, we will split it up into x and y components, and then that format and that means of defining a vector makes it really easy to deal with multiple vectors all at once, okay? That will make a little bit more sense as we get into what's called IJK notation to describe vectors. If any of you have, if for some reason any of you are like in Calc 3 or whatnot, you might have seen that. So I imagine many of you are not yet in Calc 3. You're probably in Calc 2. So yeah, that's probably about right. So, okay. All right. This one is probably, I don't want to say the trickiest one, but this is one that we are going to start using like pretty soon. Your homework assignment, I did give you one triangle like this, and I'm having you solve for another component of it. I gave you, I think it was 2 sides and 1 angle. I'm having you compute the length of one of the sides. So first off, the law of sines. The law of sines is most useful when you know a pair of opposites, right? So if I know this angle and this side, then the law of sines will help me solve some of the rest of it. In order to, when I say solve a triangle, what I typically mean is that when you're solving a triangle, you're given, so there's three sides and 3 angles. So there's 6 pieces of information that define this characteristic triangle. And so normally when you're solving a triangle, you're given 3 of them, and the idea is to solve for the other 3. And so the law of sines, bless you, the law of sines is most useful when you know a pair of opposites. So if I know this angle and this side, and let's say I know this angle, I can solve for this side pretty easily using the law of sines. The sine of this angle divided by that equals the sine of this angle divided by that. So you can solve for that pretty easily. The law of cosines is more useful whenever you have a bunch of information collected on one side. So in other words, you know these 2 sides and this angle, or you know these 2 sides and this angle, or these 2 sides and that angle. That's where the law of cosines is going to be more valuable, because if you look at the way that this is expressed, so for example, this first equation, a squared equals b squared plus c squared minus 2bc cosine of a, you're dealing with b, c, and this angle. So if you know all of this data, you can apply the law of cosines to solve for that side. So it's pretty straightforward. Does that sound good? So yeah, so law of sines works for opposites. Law of cosines works better when everything's bunched up on one side of the triangle. Okay, finally, I do want to talk about important concepts in calculus. You do need to be able to take a basic derivative, and you do need to be able to take a basic integral. We are not going to be integrating the tangent of e to the x to the 4th, from 0 to, the pi times the imaginary number. Like, it's not going to be crazy integrals. We're not doing that in here, okay? All we're doing is very basic stuff, very basic derivatives, very basic integrals. If you can differentiate and integrate polynomials, you're pretty much there. What's the derivative of x squared? 2x. Okay, what's the integral of x to the 3rd? X to the 4th divided by 4. If you can handle that, you're good. I'm being serious. I mean, You are not going to be given anything that is super relatively complicated. I mean, it's pretty straightforward stuff. The reason for these terms coming into play, I'll go backwards. Okay, so I'll tell you where integrals are going to come into play. They're not going to show up until maybe later on in the semester. We're talking about the October-November timeframe. But when we start talking about centroids, or the center of gravity, as it were, I'm sure you heard that term centroid. Like, whoa, that's kind of out there. Centroids are basically just trying to locate the center of gravity of a given body. In order to do that, you're using integrals to characterize the shape. And as for derivatives, derivatives show up when we're trying to explain the distribution of shears and moments and beams. So we won't be doing a lot of direct derivatives in that section, but understanding the concepts will make life a little easier. Okay, any questions? Okay, so I want to talk a little bit about logistics. So in terms of logistics for this remaining assignment that's due Monday, I'll go ahead and show it to you so you kind of have an idea of what it's going to look like. Let me go back to the OneDrive. I think I set this up like that. So here's the assignment. Ooh. I think it likes the zoom. Let's open in the browser. Let's do that. There we go. That's a little better. So what I've given you for the assignment, and it's going to show up as a quiz, like a timed quiz on Blackboard, but you're going to get this problem, and basically you have to determine whether or not it's dimensionally consistent. And then I've given you two trig problems. I've given you this triangle, and I want you to determine the length of C. And then I've given you this triangle, and I want you to determine the length of A. And so if you can do that, you're good to go. Any questions? Would you like 18 minutes of your life back? Unless you want to stay for another 18 minutes, I'll tell you stories and whatnot. I'm going to end class a little early for you today. Okay, I'm going to pull up the QR code in case somebody missed it for scanning. With that, I'm going to end class a little early. That's all I've got. Y'all have a wonderful weekend. I hope your first week has gone smoothly, and we will see you on Monday.